So chapter 2 is largely going to focus on vector arithmetic. First question asks you to just show me that you know how the triangle rule works. You're given vector A. It has an x component of 1 and a y component of 1, meaning that it's going to be at a 45-degree angle with a magnitude of the square root of 2. Then we have vector B, which is 2, 0, meaning it's totally in the horizontal direction. So when vectors add according to the triangle rule, they're added in tip-to-tail fashion. So if you notice, I place the tail of B on the tip of A, and then the resultant is just going to close that triangle. So I'm definitely going to ask you to draw something according to the triangle rule on your final exam. 2, compute the dot product of the vectors above. When we compute dot products, we multiply the common components together and we add. So if A has an x component of 1 and B has an x component of 1, 2 times 1 will be 2. If we do the same thing for the y components, 1 times 0, that will be 0, and 2 plus 0 is just 2. So that's how I'm getting the dot product there. Question 3, compute the angle between the two vectors in part 1. Remember that there's two definitions of the dot product. One is just that component level definition that we just did, A dot B. The second is more of a geometric definition where we take the magnitude of each vector and we multiply by the cos of theta. So what that means is if you equate those two things, you can solve for theta by taking the standard dot product, A dot B, dividing by the magnitude, mag A times mag B, that's a product of the magnitudes, and taking the inverse cosine. So if you notice, that's all that I've done in this case, and I just set it up for you because just in case I want to ask you that exact question on the final. Question 4, we're given 3 magnitudes of forces. We're asked to complete the problem below. Particularly, we want to find the resultant force. That's what I'm going to ask you to do on the final. And F1, if we look at that, we notice it's purely in the y direction, so it has no x component, and the y component is just the stated magnitude, or 320 newtons. F2, we can decompose by using trigonometry. Be careful, that angle that we're given, 45 degrees, if we get the x component, it is adjacent to that angle, so it's going to be F2 cos 45, but since it's going in the negative direction, we need to manually adjust that with a negative sign. The y component is opposite of the 45-degree angle, so it'll be that magnitude times the sine of that. And for F3, a little bit different of a decomposition because we're given the expression in terms of an equivalent triangle, 3, 4, 5. For this geometry that we're shown, the x component will just be 3/5 of the magnitude, and the y component will be 4/5 of the magnitude. Once you find each individual component, we just add up the x components and add up the y components, and that is the resultant vector. Also on the test, I might ask you to actually find the magnitude of a vector given the resultant. I might not do that since you kind of have to do that in this angle problem, so maybe just ignore that last question that I said. Question 5, definitely going to be on the test. What you're given here is a description in 3 dimensions of a vector. You know its magnitude, and you know 2 angles here. And if you think about what these 2 angles are, really one is kind of what we refer to as an azimuth or a shift in the xy plane. And then once you've shifted in the xy plane, the other is an elevation. That 60 degrees is the elevation from the xy plane. So the first step that you want to do is use the 60-degree angle in order to decompose this vector into 2 components, one along the z-axis and one in the xy plane. So you notice that the z-axis component is going to be opposite of 60 degrees, so that will be the magnitude 100 times sine of 60, and the xy plane component is going to be adjacent to 60 degrees, so I just took 100 times cos of 60. Step 2, you want to draw that down in the xy plane and then decompose it along the y and x-axis, given the angle you're given, which is 45 degrees here. Note that relative to this 45-degree angle, the x component is adjacent, so I can write fx is fxy, whatever that was, times cos 45. That's going in the positive x direction. And the y component, if I complete that force triangle, notice that it's going in the negative y direction. So it's related to the 45-degree angle. It's opposite, so I use the sine function, but I also have that manual negative adjustment. Question 6, for the vector in 5, find the angle between the vector and the x-axis. Remember that this is like our directional cosine concept that we talked about. The 3 angles that were defined as angles between any vector and the coordinate axes were alpha, beta, and gamma. For the x-axis, it was just alpha, and you could determine that by simply taking the inverse cosine of the relevant component divided by the magnitude. So we know the x component, we know the magnitude, take that ratio and take the inverse cosine. And then for question 7, writing a position vector between 2 points, 0, 1, 0, 1, 1, 0. If you think about that, they're both in the xy plane. One is purely here along the y-axis at 0, 1. In order to go to the next point, you come out 1 unit in x. So not surprising if you follow your formula of subtracting the relevant points. Remember that you need to go there from the actual tip minus the tail, that you will get just I hat or 1 I hat because you're only undergoing a displacement along the x-axis. So that is it for chapter 2, and I will see you all in the chapter 3 video.